Again, good morning or good afternoon, everyone. This first presentation is about the test design and planning using the wall of wind experimental facility. We're gonna go through the most common types of testing that we do in the facility. That includes aeroelastic, aerodynamic, destructive, and wind-driven rain test. And I'm also gonna briefly talk about the recent developments and new capabilities of the facility. I'm doing this presentation with the help of Dr. Elawadi. She's gonna talk more about the aeroelastic test and the downburst simulator that you heard a bit about it like yesterday. All right, so the existing testing capabilities, as I said, most of our testing is aerodynamic. That includes pressure tap models. We do our elastic test, wind-driven rain test, and then obviously one of the unique aspects of the wall of wind is that we can increase the wind speed up to the 157 miles per hour and do destructive test. Some recent or scheduled upgrades include the automated roughness, the robotic arm, the PIV system that is acquired through an MRI program granted by NSF, and the downburst simulator. I will start from the aerodynamic test. This is the most common type of test that we do in a wind tunnel and at the wall of wind. One example that I included here is related to the wind effects on canopies that are attached to low-rise or mid-rise buildings. This project was completed. Actually, there were like different projects associated with this testing, but we have been doing that over a period of like 4 or 5 years, and this was a very interesting codification study. What you see here on the left is the typical low-rise building with a gable roof, and attached to that building is a canopy or a patio cover or an awning, depending on which part you're coming from. You might use different definitions. The purpose of this study was to come up with design guidelines. There was nothing included in the AESC 7, and we did a very detailed study in collaboration with Concordia University in Canada. And you can see here one of the major advantages of using a larger scale. This model was 1:5 or 1:6, if I remember correctly. I think I have this information on the next slide. But one of the advantages is that we can have the patio cover or the canopy designed according to the full scale dimensions. The thickness of that element is important when we do this kind of study. When we go to scales of 1 to 100 or smaller than that, then we violate that thickness, and by using this larger scale allowed us to build a more realistic model. We were interested in both the top and bottom pressure on this element, and we have included pressure taps on both surfaces of the canopy, and the purpose was to eventually come up with a net design pressure coefficients. On the right, you see the extension of this study. After submitting the proposal to the AESC 7 committee, and finally that was approved and included in the AESC 716 for low-rise buildings, we got some feedback and we said we have to extend, we decided to extend the study to mid-rise buildings. And we did we followed a similar approach. This time we kind of like represented a typical 8 or 10-story building, and we included the canopy at the bottom levels. And we were able to move it around in order to examine different cases. Another example that I think briefly Arinda mentioned yesterday is wind loads on balconies. Again, this was initiated by interaction with industry and the damage we observed following some extreme events in South Florida. You can see the example of using different scales here. On the left, you see the smallest model that we used, 1 to 180 scale, and we started increasing the scale to 1 to 67. 1 to 25, and then we had the largest model, which was 1 to 10. By doing that, not only we are able to better simulate the geometry or consider the geometry of those very small balcony rails on the model, but also see the effect of changing the scale of the model. Another example is wind effects on elevated houses. This is an ongoing project. Both Dr. Chaudhary and Dr. Elawadi are working on that. Again, following recent hurricane events, we've seen a certain pattern when it comes to damage on this type of structure. So we did a lot of testing on smaller models or large-scale models, and we included both pressure taps, but this time we incorporated also load cells. You can see a detail on one of the footings there on the model in order to get the overall load. And the last slide on this type of testing is some sample results. That is from the canopy study, just to show you an example. By considering a lot of different geometries, we are able to put all the results together, come up with area average loads for different geometries and different configurations, and that allows us to envelope the critical values and come up with recommendations. And this is the codification process we followed in order to come up with a proposal for the ESC 7. The next group of tests is wind-driven rain test. Wall of Wind has this unique capability to introduce rain into the flow. The very first thing we need to do is obviously calibrate the flow field and rain field, basically, similar to what we do with the wind. How we do that, we have to determine the target wind-driven rain parameters. We have field data, and we select the appropriate nozzles that are placed in front of the fans. Actually, they're attached to the spires that are located in front of the fans. And by doing that, we calibrate our profile and we compare it to the field data. We have done several studies related to wind-driven rain. We've used full-scale models. We have used larger scale models, and you can see also on the right detailed view of the spraying system, the nozzles that are located on the spires. Here are some sample results. This is a study that was done by Dr. Chowdhury. We had, this is a contour plot similar to what you see with the wind pressures, but instead this shows the surface runoff rainwater distribution. What is interesting here is that the wind is approaching from the bottom left corner, opposed to what you expect when you see a pressure contour plot. So the wind is coming from the bottom left, and there was a lot of accumulation on the opposite corner of the building. This is expected. We have a flow separation and then reattachment on the opposite corner, and that's where we saw a lot of like surface runoff rainwater accumulation. And this was a very interesting finding. Another study we did was related to wind-rain intrusion on the interior of residential structures. We work on this project with Dr. Pinelli from FIT. This was challenging. We had to come up with an innovative method of measuring the flow, the rain accumulation on the interior of the building. So we decided to use some absorbent pads. We simulate different types of damage scenarios. So we had a broken window or some missing like seating or a portion of the roof. And then we performed the test and we saw how where rain goes in on the interior of the building. How we did that, after completing the test, we removed and we weighted the absorbing pads. And not only we know the amount of water that enters, but also using thermographic pictures, we saw how the water is distributed on different partitions or different walls inside the building. This is another way of presenting similar results. You have a certain breach, let's say the windows are missing on the windward wall, and you can see the flow, approximation of the flow characteristics, and then the corresponding results on the two compartments that we have rain intrusion. And here you can see some findings from a full-scale study. So what we did here is we included some instrumentation on, again, this is related to wind-driven rain intrusion, but at full scale. So we can include a camera on the inside of the interior of the model to see what is happening. And we have that basin, the catch basin drain. So we were able to compare two different cases when we have, let's say, a non-impact window and when we have a window that is equipped with accordion shutter. And you see the results on the top right. The first case is the non-impact window. And the second one is the accordion shutter. There is a major improvement when we use the shutters when it comes to rain intrusion. Then I'm gonna move into the destructive testing. Arindam, I think, briefly talked about this project yesterday. It was funded by Florida Department of Transportation. It's related to wind loads on traffic signals. Here in South Florida, this type of system, the span wire system, is very common. The components are, I have identified the different components. You can see the top, the catenary wire, the messenger wire. We have the hangers that connect the two wires, and then the signal units that are hanging from the hangers. The purpose of this project was to study the behavior of the hangers, different types of hangers, flexible or rigid hangers. Initially, we started with a short span frame in order to be able to mount it on the turntable and consider different wind directions. We performed the test. We had a lot of instrumentation attached to this configuration: accelerometers, load cells, inclinometers, inertia sensors. So it was a very complicated type of testing in terms of instrumentation. The test rig was approximately 21 feet. Obviously, this is not realistic, but we included springs at the end of the two wires in order to replicate the full span length. And in order to be able to validate what we did with the short span, we also considered a longer span. We had two columns at each end of the wall of wind walls, and that was approximately 75 feet. Obviously, we were not able to change the direction here. And then we managed to compare the findings, and there was a very good agreement between the two approaches. The video that you've seen yesterday that Arindam presented, I'm going to skip that in order to save some time. But this is the kind of testing. This is the kind of example, I would say, or a study that at the wall of wind we can see, destructive modes. We can push the the wind speed all the way up to 150 plus miles per hour and see how the system performs. And one more example of destructive testing that we have been doing over the past few years is related to pavers. This is at an oblique wind direction, so wind is coming from the right side, approximately 45 degrees. We have generation of what we call conical vortices here. Those vortices create very high suction on the roof, and you can see the damage pattern. It starts slowly to lift off those pavers. And that type of test, we also did a smaller scale with pressure taps in order to be able to do the codification study. I'm gonna skip this video. I might come back to this one after Amal is done with her part. So I'm gonna pass it to Amal for the elastic test.
Thank you, Anas. Do you hear me?
Yes.
Hey.
I'm gonna change the slides when you're done.
Okay, perfect. Yeah, thank you. Okay, good morning and good afternoon, everyone. Amal El-Awadi. I'm here to speak about the aeroelastic testing, which is one type of testing that we do at the wall of wind, and it's traditional testing in every wind tunnel. Okay. So if I want to take one step back, one assumption for the aerodynamic testing that Johannes discussed is that we assume and we make sure that the models are rigid, very rigid. So the pressure measurements are not affected by the vibration of the structure. On the other hand, we understand that structures are flexible. Some of the structures are very flexible and they experience significant aerodynamic forces generated just by the structural motion. So to account for these motions, we want to understand their elastic behavior, which is what we call the self-excited motion, which is in other terms can be called aeroelastic behavior. Aeroelastic testing is the most reliable approach, and it enables us to predict the structural deformation and possible instabilities as well. Johannes, if you please can play the video. On the previous slide, I'm sorry. Yeah. So some structures may experience instabilities like the bridge on the left, or just a long wind or a crosswind like the video on the right, due to the wind structure interaction or the fluid structure interaction. And it's not really related to the, the intensity of the wind. Just a low wind speed can generate these kind of instabilities or extra self-excited motions, like vortex shedding, galloping, and flutter, in addition to the buffeting response or the dynamic response of the structure generated by the turbulence of the wind. Okay, next please. Structural design or aeroelastic model design is quite iterative process. We have to satisfy a long list of similarity equations like scaling ratios, starting with the length scale that we chose to accommodate the model. It's basically based on the size of the testing facility and also the size of the structure. We select the mass scaling as well, velocity scaling, and then we need to satisfy the other scaling requirements with respect to the bending stiffness, the forces, torsional stiffness, and so on and so forth. I should say that this is iterative because it's very difficult and challenging to satisfy all of these requirements. So sometimes we have to, work around these conflicting scaling ratios. Okay, next please. For example, for this transmission line project, we determined the essential mode shapes and frequencies. Here, for example, 3 mode shapes. We assess the prototype frequency and the frequency scale that we choose in the beginning in the design process, and then the target frequency. So this is the target frequency that we need to obtain in the wind tunnel testing of this aeroelastic model of the transmission line. So we do our best to satisfy the mass and the stiffness in order to obtain the mode frequency, the mode shapes and the frequencies as well. Okay, next. And when I say like it's contradicting, so sometimes we do equivalent reduced scale model where we design a frame section, for example, or a section just to mimic the dynamic properties of the structure. And to replicate the geometry or the shape of the structure, we add like non-structural element, like what you see here in this case. As you can see here, there is a frame tube inside, and then the cladding, which is non-structural element, just to replicate the shape. Basically, here you can get everything out of this experiment. You can get base forces, like using these load cells here. You can get strain measurements, accelerations, basically everything about the structural behavior. Next, please. The first, in my opinion, the first thing is that you can do also system identification. That's the first advantage. So here, the blue dots here is basically telling us the frequency or the resonance response. So the frequency of the structure, you can identify that. Once I know that, I can quantify the response from any of the instrumentation, the load cells or the strain gauges, and so on. We can quantify them in terms of the peak response, the static response, in the background and resonant response. This is very important because if we go to the next slide, it's important because we can quantify the dynamic response of the structure. We can assess the code factors with respect to the dynamic response, like what Dr. Hassan Karim was telling us yesterday. We also can assess damping and aerodynamic damping for unique structures and smart materials, all these new technologies that are rising. In addition to strain measurements, like we can quantify them to assess the bending moments and shears at different sections. So basically, it gives us like everything. Okay. Now it's back to Jonas. Thank you, Jonas.
All right, so very quickly because we're running out of time. So the new capabilities. Let me change the slide here. All right, so we have added the automated roughness system. We used to do it manually, so now we can control that from the control center and change the tilt of those like roughness elements in order to simulate an open, suburban, or urban terrain. We are in the process of adding the automated 3-axis traverse system that will help us automate and do the testing much faster when we have to measure collect data at certain points in the test section, for example, pedestrian comfort type of study, where we have the wind speed probe and we move it at different locations. I'm gonna pass it again to Dr. Elawadi. I don't know if we have a lot of time to talk about the downburst simulator here.
I'm gonna discuss that in the next presentation.
All right, nice.
I would skip this, yeah.
Yes, so there is a simulation of the non-synoptic downburst wind flow at large scales for downburst structure interaction studies. And we have been working with Lehigh University and other NHERI partners in order to add hybrid simulation capabilities at the wall of wind. And the latest development, this is again ongoing. We received funding from NSF and MRI grant to add a 3-component particle image velocimetry system in order to enable fundamental research in wind engineering and other disciplines and fluid mechanics. This is a very complicated system, considering that we operate a large facility and it's also like an open facility. So there are like a lot of challenges associated with that. We're in the process of commissioning the system. So this is again an ongoing process. We have received some of these components that you see in this sketch, and the installation will start in fall. And hopefully we'll be able to provide this capability to users as of next year. Thank you very much. And I will be happy to answer any questions you might have.